Thank you. We're at least on the same page. Okay, so this is going to be the second half or the second three quarters of this lesson. We've got a lot to cover today. Okay, so we're going to try to hustle through this. This is area between curves, part 2. Area between curves. Remember that tomorrow is a work day on the 6.1 assignment. So if we don't get all the way through this lesson, it'll be fine. I'm not going to panic or have the heebie-jeebies. We'll just finish the last example tomorrow, and then you can have the rest of the class period for work. Okay? We're going to start with example 4, and it says this is the area between two velocity curves. Well, what do you know about the area under one velocity curve? What is that? Position, displacement, right? So if I'm looking for the area between these two curves, well, let's read the problem. It says the graph of the velocity in feet per second for two cars, A and B, that start side by side and move along the same road. So they start side by side, they move along the same road. A table of values showing the velocity of each car and the difference in velocities at 2-second intervals of time. So the difference in velocities, they're not racing. We've got two cars side by side on the same road with a difference in velocities. Really? And we're trying to figure out what's the difference in the curves. Okay, first of all, what does the area between the curves represent? That's going to be the distance covered. It says use a midpoint Riemann sum with 4 equal subintervals to estimate the area over the interval from 0 to 16. So what are we finding?
How much farther one went than the other.
How much further one went than the other after 16 seconds on this road where they are traveling side by side but at different velocities safely. Are we understanding? Yes? So we've got to use 4 different subintervals here. 4 different subintervals. And it wants us to look, we're going from 0 to 16. So if we're dividing 0 to 16 into 2 different subintervals, how long is each interval? 4 seconds. 4 subintervals on the area from 0 to 16. So 1, 4. Use a midpoint sum with 4 equal subintervals. So the midpoint, I think we've forgotten how to do this. B minus A over 2. This is delta X. Right? And we're on the interval from 0 to 16. So 16 minus 0 over 2 means each interval is 8. Not over 2. Why did I divide by 2? Divided by 4. Each interval is 4 long. Okay? And we're using a midpoint Riemann sum. So on the interval from 0 to 4, what's the midpoint? 2. And in between 4 and 8, what's our midpoint? 6. And in between 8 and 12, what's our midpoint? And in between 12 and 16, we're using the value of 14. Can you understand how this just worked? Okay. So when we write our Riemann sum, we're going to have delta x times f of the midpoint value. So you could say 4 minus 0 over 2. You could split it like that. Plus delta x times f of 8 minus 4 divided by 2. Right? So that's how we're finding that middle value. Are y'all following that? I think it would be best to do delta x is 4. And it's 4 every time. so we can factor that number out. And we just split the difference between, it would be 4 plus 0 over 2, averaging these two numbers. 8 plus 4 is 12, divided by 2 would be the 6, plus delta x times f of 12 plus 8 over 2 would be 10, plus delta x times f of the last one would be 16 plus 12 over 2. 16 and 12 is 28 over 2, which is going to be the 14. That's how you decide what numbers to use. It's harder on paper than it is to just split them. Anyways, once you know what numbers to use, delta x is the same every time. So that's the 4. I'm saying factor that guy out. And use f of 14 over 2, or 4 over 2 is 2. So I'm going to go to this number right here, 13. Plus, don't close parentheses. We've got a whole sum in here. Plus 23 plus 28 plus 29. So 4 times 13 plus 23 plus 28 plus 29. Do y'all see where this last column of information is coming from? The velocity of car A minus the velocity of car B.
Oh, that's really convenient.
They already computed that for you, so you don't have to do that part. 13 plus 23 plus 28 plus 29. Spoiler alert, 4 times whatever that number is 372 feet. 372 feet. So what does that tell me?
How much farther one traveled?
How much farther car A is than car B in that 16 seconds. Okay. I thought this one was important to not skip because it's been a long time since we walked through a Riemann sum. It's been a long time for me too. You understand the midpoint idea? Okay. All right, let's go on to example 5. It's a whole new context, whole new problem. This is example 5, and this is a measles pathogenesis curve. You guys are of the age where you remember COVID and how we were trying to flatten the curve. This is that curve. This is the spread of a measles contamination of some sort. It shows how the disease develops in an individual with no immunity after the measles virus spreads to the bloodstream from the respiratory tract. So this is in one individual, how the measles virus is kind of attacking that person. But we talked about when we were dealing with this curve in a population that if we would do some different things, we could slow down how it was traveling through the population. Okay, here, I think I relate this to the flu. My kiddo just had the flu, and I feel like she was much worse. She got it on Wednesday. She was much worse Thursday, Friday, Saturday. And by Sunday, her symptoms had kind of tapered off, but she was still contagious. If y'all remember, on Monday, she still had fever. She was feeling fine, but she was still contagious at that point. So that's kind of how this looks to me. This is a measles virus. We also have a function for this virus. That's going to be on this next slide. Okay, so right here it has a function. It says if infection begins on day 1 or on day T1 equals 10 and ends on day 18, what are the corresponding concentration levels of infected cells? So they want us to measure the area under the curve on T10 through 18. So these are days of infection. We're trying to measure the area underneath this function. And it says the level of infectiousness for an infected person is the area of the region bounded by the graph below the line and through these 2 points, through point P1 and P2.
Find the slope of that and evaluate that line.
Correct. So we need to find the slope of that line. We can write the equation of that line, and then we can find the remaining area between the curve and that line. Is that making sense how we're going to do this? Okay. So what I would do on your calculator is I would put this function into your F1. Put this function right here into F1. Why not? This is not my favorite example, by the way.
I could -1 or no.
Yeah, no can.
You couldn't do it either? I can't do it. Okay, I can't do it.
Did you do negative x times
Yeah.
x minus 21 times x plus 1?
Yeah, we had to distribute it
Why? Why can't you just type it as fractions?
because our calculator don't like it as fractions.
So you're gonna accept
I mean, this-
input.
Put multiply between the x and the first parentheses.
Yeah, put an x times.
I was gonna show you.
Between the x and the first parentheses, you should be able to just put times.
That works.
Should be able to just put times in there. We need to write the equation of the line that passes through these 2 points. This is why I'm having you do it on your calculator. Let's find the slope between those 2 points. So you're going to have f of 18 minus f of 10 over 18 minus 10. And let's get a good number for that.
My 8 looks like a 2.
We've just got to write this equation. That's all. F of 18 minus f of 10 over 18 minus 10. This is going to be m for that secant line. M equals negative 23. Cool beans? Okay, now we got to write an equation. I would use y equals mx plus b. It's linear. We know m is negative 23. If x, somebody type on your calculator f of 10. If x is 10, what's y?
1,210.
Okay, so 1210. So we've got 10 comma 1210 as a point. Not interested in the other point right now. I just need 1 point to write an equation. So we'll say 1210 for y is equal to negative 23 times 10 plus b. I'm trying to get a good b value here. We have a b value yet? Seth, did you get a number?
Negative 52.61.
For b?
I got 1,440.
That's what I got, 1440.
Yeah. Because you don't divide it, you just subtract.
Yeah, you just add
Actually.
add 23 times 10.
Yeah.
I don't know what that is. 23 times 10. It feels like
I
230.
forgot the
30?
10.
Right, we're just adding 230. Okay, y'all, I'm telling you, something's wrong with me today.
I forgot to add the 10.
So this is 230. Now, look, we add them up on paper.
I was like, what?
Okay, so for me, then I'm going to put that equation in F2. F2 of x is going to be negative 23x plus 1440. There's the function. That's the equation of this secant line. Is that making sense? And so then we're going to be able to integrate on the interval from 10 to 18. What's my high function? F1
Yeah.
minus F2 of x after you put the line in there.
Oh, no.
The hardest part of this was the algebra 1. Can I write the equation of a line given 2 points? No. Fail. I don't know if y'all watch Bluey or not, but that's my life right now. Fail.
What am I doing? Hold on.
Yeah, got it.
I did it.
In years past, I've had my kiddos do this one by hand. So, but I think we need more practice on the calculator.
Easy.
What'd you get?
1,877.32.
1,877.333, it's repeating, cells per milliliter of blood per day. So this is a contagion rate. Why did I say it was a rate?
Because it's changing.
It's the area under the curve. Ah. You did?
I did.
Woo!
It's cell for what?
Cells per milliliter. The level of infectiousness for this patient. If you look at the top of page 483, you'll see all of this handwork. I just decided that we needed more practice putting it in our calculator and being accurate there. Okay. Any questions on this particular example, example 5? No? Okay, so now we transition to a better part of this lesson. I did not like example 4 or 5. Just for whatever it's worth, those were not my favorites. But I do like what's coming. Okay, so let's look at this picture. It looks like a candy-wrapped bow tie thing, right? This is at the top of, or the middle of page 483, in the middle. Maybe you have wondered, what if I'm on an interval that includes the functions changing high and low? Okay, so up until this point, on the other day, whenever we were doing this, we would have integrated from here to here. And we would have chopped it off and we said, I want to find the area of the curve bounded by these two functions, right? And we would have found where they intersected and we would have stopped right there. But what if that interval stretches out just a little bit further and we don't just bound it by where the two functions intersect, but we exchange high and low?
It flips.
It flips.
Which one's on top?
Right. It flips which one's on top. And we know that subtraction is not commutative, so it's going to end up making a big difference, right? So how do we handle that?
We split it up into 3 different parts.
Okay, so there's one option. We find where they flip-flop. We integrate with high minus low on this interval, and then we add this one high, this one low on the next interval, and then we do another integral, high minus low, which we're going to do in just a minute. Or the alternative version is to stick it in your calculator, and what would handle the fact that they're flipping over and over? A computer would, but no. What else? We had to deal with displacement versus distance. Yes. When we were trying to find the area under the velocity curve, the net change, we said, is displacement. But if we wanted total distance, total area, regardless of which function was on top, we did absolute value. That's what this calls for. This says we can either do f minus g when f is greater than g, and g minus f when g is greater than f, right? They kind of made a little piecewise function here. Or you can use your calculator and take the absolute value of f minus g. And it will handle the fact that your functions are changing, which one's on top and which one's on bottom. Do you understand what it's saying?
One seems easier. than
One
the
seems
other.
easier. Okay, well, the handiwork is not fun. But does it make sense to you? Do you understand the need for changing? About 3 of you. Give me a Okay, so this is example 6 down here at the bottom. And we're going to work it on a blank paper, but I want you to have it written down. It says, find the area of a region bounded by the graphs of y equals sine x, y equals cosine x equals 0, and x equals pi over 2. We're going to draw a beautiful picture. I'm pumped about this problem. I really like this one.
Oh, yeah, this is really cool.
It's going to be cool looking. I was not a super fan of the last 2 examples, but example 6 gets me really excited about life. This is where it's at for me. It's tricky, it's calculus-y, it doesn't have measles. You got it? Got it written down? Okay, your first thing that you're going to want to do here is draw it. You have to draw a picture. Okay? If you don't draw the picture, you're not going to have a clue. So we're bounded by 3 functions, or 2 functions, but on an interval. So our first function is y equals sine of x. So I'm going to draw that. And we're going from 0 to pi over 2, so I'm not interested in anything to the left of the y-axis. So where does sine begin? What is sine of 0? 0. Okay, let's go. We're going only to pi over 2, so I'm going to let that be over here. Sine of pi over 2 is at the top of my circle, right? Did y'all unit circle yesterday a little bit?
We did big unit circle.
We did big unit circle. So at the top, pi over 2, what is sine? 1. Okay, so this one's going like this. Let's carry it out to pi, just because I need to. What is sine of pi? 0. So this function looks like this. It's going to come back down. So you can imagine this is a half cycle, and it's pretty stretched out here. Cool? Okay. The other one that we have to plot at the same time is y equals cosine of x. Where does cosine start when x is 0? Cosine of 0 is 1. Cosine of pi over 2? 0. And cosine of pi?
Is
Negative 1. Again with the half cycle. Okay, so if you're expecting it to come back up, it's just not quite there yet. Yeah? Okay, now we want to compute on the interval from 0 to pi over 2. And we want to know what's the area between the 2 curves. And I want to think about 2 different ways to solve this problem. Take the area of all of it and subtract. Okay. So you could throw on your calculator the integral on the interval from 0 to pi over 2 of the absolute value, and you just pick one to be the top. You could say of sine x minus cosine x dx. That will compute on your calculator. That's one option. Okay? But when you're working by hand, that's not an option. So now we're left to busting it up. And the question that I have for you is, where does this change occur? Just because it's halfway between 0 and pi over 2? Probably. Reason with it. Why? Why is that exactly where the change happens?
Because they're both equal there.
Because they're both equal there.
Yeah,
What are they both equal there? Square root 2 over 2. This y value, where they're both equal, is square root 2 over 2. Good. You've come full circle. Okay. So we can integrate on the interval from 0 to pi over 4. what's going to be on top? In this interval, we're going to have cosine of x minus sine of x dx. And then plus, what else?
The interval of pi over 4 to 2 pi over 2 of sine x minus cosine x dx.
Pi over 4 to pi over 2 of sine x minus cosine x, because now sine function's on top, dx. Do you understand what's happening here? Oh, I wish I had more space for this. All right, what's the antiderivative of cosine?
Negative, no, sine, just sine.
Sine.
It feels weird not having like some stuff.
What's the antiderivative of sine x? Why do we not have to substitute?
That's the scratch pad in your top.
I have no idea when we paused recording. None. But it paused a good while back.
Oh no.
Poor Rebecca. Becca, if you want to come in, I'll work with you on this particular problem if you don't catch all of this while it stopped recording.
Just the clip notes.
Mm-hmm. Anybody got a number? .828. Is it the same as square root 2 square root 2 minus 2? Yeah. What else could we have done? There's one more thought. Something that would have really, really, really saved our bacon.
If we added the areas and then subtract that little area underneath, I don't know.
Ooh.
I don't know.
But that's two different functions. That would be yuck. Anybody think of symmetry here?
Yeah.
Anybody see a butterfly out of this looking guy? Looks like a butterfly to me. You could have done 2 times the integral from 0 to pi over 4 and just chunked half of it. That would have saved you a lot of time and effort in dealing with the trig. Okay. Questions on that one? Did we get lost in the trig part? You hung in there? Yay.
Trying to figure it out.
Good. Good, good, good. All right. So here's our last thought for today. And we're going to probably have to work example 7 tomorrow. I just don't think that, I don't know. Do you have it in you? Do you have it in you to work one more? Okay, well, let's give it a try. We'll see. It's been a long 2 class periods is where I'm at.
No, I think so.
We're gonna try.
Example 7 is the last example for today. I mean, it's the last example for this whole lesson. I just don't know if we can get it done today or if we need to hold off and do it tomorrow. You think we can do it today?
Yeah.
We got 10 minutes.
Got it.
All right, all right. Y'all perk up. Breathe. Take in some air. Okay, all right. That was good. Okay. Okay, so look at this picture here. This is kind of a wonky set of 2 functions. It says sometimes it's easier to find the area of a region by writing x as a function of y instead of y as a function of x.
Swap them.
You can swap them. This is so cool because we're looking at, Thomas is making a face like, I don't like it. I don't want to. It's so cool because sometimes it's easier to measure area from left to right than it is from bottom to top. If it's not clear to you what's the bottom of this function or where should I integrate left, sometimes it's just real hazy. And so if you'll flip them, you can still find the area, right? If I say, what's the area of this rectangle? Isn't it the exact same area as this rectangle? Right? So if I can look at it from one way and then turn it, now all of a sudden I can handle it better. The rule here is the same. You still want to do high minus low, except if I'm dealing in x, what's the high side?
The farthest right.
The furthest right. So in x, you'll have right minus left. Notice that it now says dy because I'm integrating with respect to y, not with respect to x. Okay, so now that dx, dy thing is very important because it tells me what we're talking about. What variable are we integrating with respect to? Yeah?
Yeah.
Okay, let's try. Come on, come on. Example 7. Example 7, it says, find the area of the region enclosed by the graphs of the line y equals x minus 1 and y squared equals 2x plus 1. Okay? The first thing we want to do here is we want to graph them. We want to graph them, and then you'll understand why it's easier to go the other way. So first, my first function here is y equals x minus 1. What does that look like?
Oh, it's just a linear
Oh,
line.
it's just a linear line.
Of course, it's a lot.
Graph it.
Well, we need both sides of the y-axis.
Yeah. The other function is y squared equals 2x plus 6. Y squared equals 2x plus 6. That is y equals square root. Is that what you're going to say? Of 2x plus 6. I used to teach you to graph square root functions by deciding what you liked square roots of. I like square root of 0, the 0. I like square root of 4. So if we set the inside equal to those numbers, we can figure out what x should be, right? If I say that 2x plus 6 needs to equal 0, x equals negative 3. So at x equals negative 3, y is 0. You remember doing this before?
Yes.
I know what the square root of 1 is, so I'm going to set 2x plus 6 equal to 1. Minus 6. That's not nice. 7 halves. Negative 7 halves. Which is what? Is it? Negative 5 halves. That's negative 2.5. Comma 1. Yeah, that'll work. Negative 2.5, comma 1. We're handling plus and minus at this point. Let it be plus or minus the square root so you can plot both. If I let 2x plus 6 equal 4, negative 2 divided by 2 is negative 1. X equals negative 1. Output is what? 2. The square root of 4 is 2. Ah, we hit a dot on our line. If I let 2x plus 6 equal, what else? I like to take the square root of 9. Three halves. So at x equals 1.5, the output's 3. Let's get it graphed today, and we'll finish the problem tomorrow, okay? But let's finish graphing. We need to take the square root of not 9, but what's next? 16?
Do we need the exact point? If we
We need the exact points.
collided with the...
We got to collide on the other side. 5. 1, 2, 3, 4, 5, comma 4. 1, 2, 3, 4. There we are. I would like to pick up here tomorrow where you have both functions graphed with intersections.